Hello friends, myself Dr. Nandakumar Rao Bawale, College of Engineering, Ambazogai, going to deal with Applied Thermodynamics 1, our 24th lecture. So, in last lecture, we have discussed about numerical on vapor power cycle. Same thing we are going to continue in this lecture, numericals on vapor power cycle. Today we will discuss about a numerical related to modified Rankine. So now we'll see what is given in this problem. Steam engine takes dry steam in the sense dry saturated steam, where dryness fraction of steam X is equal to 1 at the inlet of engine at a 20 bar pressure. So pressure of steam P1 is 20 bar and exhaust at 1.2 bar. So that is back pressure or condenser pressure, we can say this as PB as 1.2 bar. The pressure at release is 3 bar. So pressure at release in the sense, so this steam is not expanded completely in modified Rankine cycle. So this expansion is stopped at pressure P2, that is P bar. Then he is asking us to find out theoretical loss of work per kg of steam. Work is lost. If expansion is complete from 20 bar to 1.5 bar, then complete expansion is there and that is going to develop larger work, whereas if expansion is stopped at pressure of 3 bar, so expansion is restricted at 3 bar only, then the work done per kg of steam is lost. So there is incomplete expansion in modified Rankine cycle. Due to incomplete expansion, some work is lost. So how much of work is lost theoretically due to the modification in Rankine cycle, and loss in Rankine efficiency due to restricted expansion. So how much work is lost, and depending on that we want to find out efficiency loss due to the modification in Rankine cycle. Now let us see the Rankine cycle. So here the steam enters into the steam engine at pressure P1 is equal to 20 and dry saturated, that is condition of steam at x1 is equal to 1. At point 1 steam enters into the engine, has got condition as dryness fraction x1 and pressure P1 is equal to 20 bar. So that is shown here on TS diagram. So point 1, at this point 1 pressure P1 is nothing but pressure P1 is 20 bar. At 20 bar steam enters into the engine and then that steam is isentropically expanded up to pressure of 3 bar. So at this you can say pressure is P is equal to 3 bar. So at 3 bar expansion is stopped and steam is exhausted. So here the steam is expanded from 20 bar to pressure P2 is equal to 3 bar and suddenly the exhaust valve is opened at point 2. So if the steam is expanded from point 2 to 3, sorry 2 to 2 dash, then we call it as a complete expansion. So here the expansion is restricted at point 2 and steam is allowed to move directly into the condenser. So this condenser pressure PB is also given. PB is equal to 1.2 bar. So 1.2 bar. So then it is allowed to pass into the condenser at pressure of 1.2 bar. So here this 2-3 process is nothing but a release of steam into the condenser is at pressure of back pressure of that engine, or we can call this as the condenser pressure PV is equal to 1.2 bar. Then steam is condensed, again it is heated. So in this problem one more thing is to be noted. So the pump work is neglected. The pump work is neglected. Already it was supposed to be written here. So neglecting pump work, this cycle is now here. Say for example this is 0.4, this is 0.5. So from 0.4 to 5 sensible heat is added 5 to 1. certain heat of vaporization is added and the cycle is repeated. So here the work is done from point 1 to 2 in case of modified Rankine cycle. If it is not modified, then work is done from point 1 to 2 dash. Here we will have two works, work 1, work done 1, work done 2. So work done 1 means the work done in the actual Rankine cycle from 1 to 2 dash, and work done 2 means the work done in a modified Rankine cycle. So now coming to the data given, what is given and what we have to find out. This problem can be solved by two methods, one by using steam table analytically, another one by using Mollier chart. Now coming back to the data given. So P1 pressure of steam when it enters into the turbine engine is 20 bar and drainage fraction x1 is equal to 1 because it is dry saturation. And pressure at release is 3 bar and then condenser pressure is 1.2 bar. Then he is asking us to find out loss in Rankine efficiency and work loss. So now what we want to find out is work done in two cases. Work done in two cases, work done per kg of steam with complete expansion. Expansion is complete without any restriction of expansion. Then work done is given by H1 minus H2 dash. We can see in this diagram, H1 is the enthalpy at point 1, H2 dash is the enthalpy at point 2 dash. H1 minus H2 dash is the work done in a cycle if the expansion is complete without any restriction from 1 to 2 dash. But in case of modified Rankine cycle, work is restricted. So expansion is restricted. Work done per kg of steam with incomplete expansion. So expansion is incomplete. Then this work done is given by H1 minus H2. H1 minus H2 work is done from 1 to 2. So H2 is enthalpy at point 2. But after this point 2, this steam is exhausted directly into the condenser. Here pressure is going to be changed, whereas volume remains same. So here constant volume process, 2 to 3 is constant volume process. So during constant volume process, we have to find out PdV work, P into dV. So sorry, VdP work. Volume is same, VdP work has to be obtained. So that VdP work is given by V is the specific volume of steam and change in pressure dP. Change in pressure is P2 minus of PV. So P2 is the pressure at point 2, so which is 3, and PV is back pressure 1.2. Difference is taken a specific volume into change in pressure, that is V into dP. Volume is constant, change in pressure P into P2 minus PV. So this gives us VdP work. Here from this pressure P is in bar, so that is to be converted into what you call kilojoules per that is to be converted into kilonewton per meter square. So 10 to the power 5 and then dividing it by 1000, we get this work done in kilowatt, or sorry, kilojoules per kg. So for that we have to multiply it by 100. So now Rankine efficiency 1, if without modification, work done divided by heat supplied. Heat is supplied from H4 to H1. So at point H4, condition of the substance or liquid is water. So here we call it as HF4. From point 4 up to point 1, heat is added. So heat supplied is H1 minus HF4. So work done divided by heat supplied gives us Rankine efficiency 1. Then Rankine efficiency 2, work done divided by heat supplied again. Then loss of work. So here we obtained work done 1, work done 2. Work done 1 minus work done 2 divided by work done 1 gives us the loss of work. And then Rankine efficiency 1 minus Rankine efficiency 2 divided by Rankine efficiency 1 gives us loss in Rankine efficiency. Now we will start to solve this problem by two methods. So first we'll have the data from steam table. So data from steam table at 20 bar. So pressure at 20 bar, saturation temperature 212 volt, specific volume of liquid is 0.00117, and enthalpy of liquid is 908, then latent heat of vaporization is 1888.6, then entropy of liquid is 2.4469. So this entropy of vaporization is 3.88. All this is taken from steam table at 20 bar, 3 bar and 1.2 bar. So this is at pressure P1, that pressure P2, that pressure P3. So now let us start to solve this problem by two methods. So very first what we have to find out is, in this problem we can find out H1, then we can find out H2, then we can find out H2 dash, then we know P2, PV, Vs has to be taken from steam table, and rest of the things we can find out. So very first our duty is to find out H1, H2 dash, H2. So to find out H1 is very simple, but to find out H2 dash and H2 we must know the dryness fraction. If we see here, H2 dash, enthalpy at point 2 dash is equal to HF plus X2 dash at 2 dash point, HFG at point 2 dash. HF2 dash we know HFG2 dash, because at pressure of 3 bar we know HF and we know HFG. So if we see in this table, so here this is at pressure point 2 dash. Point 2 dash is at pressure of 1.2. Every data is known. We can find out it from this table, and but only one thing that we do not know is dryness fraction. So again, to find out H2, we must know HF at 2 plus X2 and HFG at point 2. So at point 2 dash, at 2 dash, pressure PB is equal to 1 point, and at H2 point pressure is P2 equal to 3 bar. So this data HF2 and HFG2 can be taken from steam table at 3 bar. And here HF2 dash and HFG2 dash is taken at pressure of 1.2 bar from steam table that we have written already. So to find out this H2 dash, we must know the value of X2 dash. And to find out H2, we must know value of. So for analytical methods to find out, we must know X2 dash and X2. But if we want to solve it graphically using a Moliere chart, then we need not to find out X2 dash and X2. So we will solve this problem by both the methods, and we will know what is the difference between two methods, and what benefits we get if we use Moliere chart, and what are the demerits. Now coming to this Moliere chart, first we will solve it using Moliere chart. So what is given in the problem is, the steam is expanded from 20 bar and dry saturated. So this pressure is shown here, 20 bar. So 20 bar and dry saturation. This curve is dry saturation curve. So this point is located here, point 1. Steam is expanded from point 1 directly to the pressure of 1.2 bar. So here this curve is representing 1 bar pressure, and this is representing 1.2. So 1.2 bar is between 1.5 and 1 bar. So somewhere here in between there may be a curve. So we approximately assume that it is at the center of these two curves. So this curve is somewhere here. So we assume this curve of pressure 1.2 bar is here. So if we expand steam from 1 to 2 dash directly to back pressure of 1.2 bar, so this point 2 dash is located. So meanwhile, point 2 has to be located at pressure of 3 bar. So here we can find pressure of 3 bar. So this line indicates the pressure of 3 bar. Wherever it intersects, this point is marked as point 2. Point 1, 2, 2 dash we have marked down Moliere chart. So from this Moliere chart, directly we can get enthalpy at point 1, enthalpy at point 2 and enthalpy at point 2 dash. We need not to remember any formula to find out the results. So first of all, we'll find out the values at point h1. So if we find out enthalpy at point 1, so it is 2800 kilojoules per kg. So we can see here corresponding to this point 1, enthalpy is 2800 kilojoules. So we'll write this enthalpy h1 is equal to 2800 kilojoules per kg. So this is from Molière chart. So again, corresponding to point 2, if we see here, so enthalpy will be 2450. Just it is above that, we can say it as 2460. Enthalpy at point 2, here is H2, here is H2 is equal to 2460, we can write 2400 H2 2460 kilojoules per kg. Then enthalpy at point 2 dash, enthalpy at point 2 dash is approximately above this 1300, so it will be H2 dash. So H2 dash is 2320. 2320 is H2. 1020 kilojoules per kg is the enthalpy of steam at point 2 dash. So coming to this work done 1 for incomplete combustion, sorry, incomplete expansion, work done for complete expansion, we call complete expansion in kilojoules per kg is given by H1 minus, so expand steam from 1 to 2 without any restriction 1 to 2 dash. Work done is given by H1 minus H2 dash. H1 is 1800 minus H2 dash is 2320. So from this 1800 minus 20, this gives 480 kilojoules of work per kg is work done 1. So now work done 2, work done for incomplete expansion of steam in kilojoules per kg given by, so incomplete expansion means from 1 to 2. This is difference of H1 minus H2 plus of specific volume of steam at point 2 into Pb minus, sorry, P2 minus Pb into 100. So this gives us the work done by the engine if the expansion is incomplete. So if the work is done by incomplete expansion, the work will be less than the previous work. Work is lost in the second case. So here we can write this enthalpy at point 1. H1 is equal to 1800 minus of H2 is 1460 plus of specific volume at this pressure is given by from this steam table. So Vf is the liquid volume. So here this is pressure of V bar from steam table at pressure of 3 bar. Volume is 0.605. 0.05 into P2. Pressure at point 2 is 3 bar minus of 1.100. So this is 10 to the power of 5. Actually pressure P is bar. So this is, for example, 3 into 10 to the power of 5 divided by 1000 to convert it in kilonewton. So this 1000 and 5 gets cancelled, remains 2. Means 3 into 100. 100 meter here. Converting this bar into kilonewton per meter square multiplied by 100. So now on simplification, get this work done as V minus of 1.2 0.5 plus 4 448 448.9 kilojoules per kg the work done and call this as a work done. So now we know work done 1, work done 2. So heat supplied we can find out. Heat supplied is equal to H1 minus, we can call this point as 4. H1 minus HF. Already we know H1. HF4 can be taken from steam table at pressure PB is equal to 1 point bar. At 1.2 bar. So this HF value is nothing but HF4. HF value at 0.4 at pressure of 1.2 bar from steam table can be taken as 439.4. HF4 is 439 kilojoules per kg. The H1 value we know. H1 value is 2800 minus HF4 is 439.4. This gives us heat supplied in per kg. 2800 minus of 439.4. So 2360 0.6 kilojoules per kg. Now we know work done 1, we know work done 2, we know heat supplied. We can find out Rankine efficiency 1 and Rankine. For Rankine efficiency 1, Rankine efficiency equal work done 1 divided by heat supplied to 100. work done 1, which is calculated as 480 kilojoules per kg. 480 divided by heat supplied, we have calculated as 2360.6. 300 into 100. Rankine efficiency 1 as Pt divided by 2360, 20.33%. 0.3% Rankine efficiency 1. So Rankine efficiency 2 is equal to work done 2 divided by heat supplied. Work done 2, if we see, work done 2 is 448.9. 448.9 divided by heat supplied is say 230.600 gives 448.9 divided by 300.6, 19.016%. So now we know work done 1, work done 2, Rankine efficiency 1, Rankine efficiency. So now we can find out. First we'll write down work done 1. Value of work done 1 is 480 kilojoules per kg of steel. Work done 2, 448.9 kilojoules per kg. Rankine efficiency 1, 20%, 20.33%. And Rankine efficiency 2, 0.01%. Loss of work in percentage loss of work can be obtained by work done 1 minus work done 2 divided by work done 2. So generally loss means it is the work which is reduced from 1 to 2. So it is compared with respect to work done 1, 200. Work done 1 is 480 minus 48.9 whole divided by 40 into 100 minus 448.9 divided by just 0.47. 47% of work is lost. Percentage loss, Rankine efficiency equal to Rankine efficiency 1, Rankine efficiency 2 divided by Rankine efficiency 1 into 100. Rankine efficiency 1, 20% 0.3% minus Rankine efficiency 2 is 19.1% whole divided by 20.100. point minus 0.01 divided by, this will be 6.49%. 49% the loss Rankine efficiency. Approximately Rankine efficiency, loss in Rankine efficiency, work done same, because the work done going to be different, but heat supplied is same. So definitely the loss in Rankine efficiency is very similar to the loss in work. So absolute loss in work is different. Absolute loss in the work is work done 1 minus work done 2 gives us absolute loss in the work. How we can calculate the work done as well as Rankine efficiency using Fourier chart. So here it was very simple for us to find out enthalpy at point 1, enthalpy at point 2, enthalpy at point 2 dash using Fourier chart. So only thing is we must know how to identify, how to locate point 1, then how to 2 dash, how to utilize this Fourier chart. Now same problem we will simplify using this what we call as steam table. In this steam table, solve this using steam table. We want to find out enthalpy at point 1. Enthalpy at point 1 can be obtained as HF1 of X1 HF1. HF1, this is at pressure of P1 to 20 bar. So at point 1, P1 pressure P1 is equal to Reynolds fraction X is equal to 1. So HF1 and HFG1 can be taken from steam table directly. X1 value is given. So from steam table, if you add this at 20 bar, HF1 is 908.77 and 88.6 HFG 908.77. 908.77 plus X value is 1, Reynolds fraction is 1, 188 point, HFG1 is 1888 point, that fraction HFG1 is 1888 point. From this we can calculate H1 value. So 908.77 plus 1888.6 gives us 2797.37 kilojoules per kg. So this is using steam table, and I write here in bracket H1 is equal to 2800 was obtained using Fourier chart. Was the value 2800 was the value of H1 we have obtained using Fourier chart, that we can see. One is 2800 which we obtained by using Fourier chart. So here in this Fourier chart H1 value was 2800. Now to find out the value of H2 H2 dash it is not so easy. So here to find out value of enthalpy at point 2 H2, we must write formula HF2 plus of H2 and HFG2. So HF2 HFG2 can be taken from steam table at pressure of P2 is equal to P bar. So at point 2 pressure is P bar. So HFG2 and HF2 can be taken, but what about X2? We don't know X2. So X2 has to be obtained. Similarly, H2 dash, enthalpy at point H2 dash can be taken as HF2 dash plus X2 dash HFG2 dash. That pressure PB equal to 1.2. HFG2 dash and HF2 dash can be taken from steam table at 1.2 bar. What about x2 dash? What about x2? First of all, we have to find out value of x2 dash and x2, and then only we can find out h2 and h2 dash. So for that, we must see this process of expansion. So process of expansion 1, 2 and 2 dash is constant entropy process. So it is adiabatic process. Adiabatic process entropy remains same. The entropy at point 1 is equal to entropy at point 2 is equal to entropy at point 2 dash. So here we can write equation as S1 is equal to S2 is equal to S2. The entropy at point 1, this is that pressure equal to 20 bar. This is that pressure bar. That pressure 1. S1 is at 20 bar, S2 is at 3 bar, and dash is at 1.2 bar. So these values are at 3 different pressures. S1, we will write equation for S1. So this we write as SF1 plus X1 SFG1. These values are taken corresponding to pressure of 20 bar, which is equal to S2 entropy at point 2 can be written as SF2 plus X2 SF. So these values are taken at pressure of values are taken at 20 bar. These values are taken at 20 bar, and then SF2 dash plus X2 dash SFG dash. These values are taken at pressure of 1.2 bar. So now SF1 X1 value is known because X1 dryness fraction at point 1, X1 is equal to 1. So SF1 SFG1 can be directly taken from steam table. So these values can be taken from steam table. Equating first two terms, we'll get X2 value. Equating first and last term, get X2. So now we'll take first two terms. First two terms we will take at 20 bar and 3 bar, and we'll simplify. We'll find out x2 value, then we'll find out x2 dash, then we will come back to 2 dash and h2. So taking first two terms, sf1 plus x1 sfg1 equal to sf2 plus x2 sfg2. So this is at pressure of 20 bar, that pressure of values from this in table. Already we have taken data. So at 20 bar, SF is 2.4469 and 3.889. Here, these values we will take directly there. Pressure of 20 bar. That pressure of 20 bar, SF value is 2.49 plus of dryness fraction x1 is equal to 1 to SFG1 at 20 bar, 1 as 3.8898. 0.898 equal to SF2 at 3 bar pressure, 3 bar from steam table. Coming back here, 3 bar is 1.6712, 1.6712, and SFG is 5.3201. These two values we take now table. So here this SF2 value is 1.6712, 1.712 plus of x2 which is unknown, and then SFG is 5.3201, 5.3201. These values are taken at 3 bar. These values are taken at 20 bar. So here unknown is only x2. Simplifying this equation, we get x equal to dryness fraction of steam as 4, 9, 9, 8, 7, 1, 2, full divided by 5.3201. This gives us dryness fraction of steam as 0.87. Then coming the dryness fraction of steam at 0.2 dash. So this 2 is dryness fraction 0.2, which is 0.876. 876 is dryness fraction at point. Once we know dryness fraction at 0.2, we can find out enthalpy at 0.2. So again, for finding dryness fraction at 0.2 dash, so now we equate second two terms. First term and last term we equate. We try to find out. So here SF1 plus X1 FG1 pressure of 20 bar equal to SF2 dash plus 2 dash FG dash. That pressure of 1 point, values of SF1 nothing but again 2.4469 plus X1 value is given as 1, SFG 3.8898 equal to SF2 dash from steam table we have taken at 1.2 bar. Back here 1.3610, 5.93, that pressure of 1.2 bar. Coming here, write this value at 1.2 bar, pressure of 1.2 bar. One point 3610 point plus of x2 dash which is unknown into SFG 2 dash at 1.2 is 5.9370, 5.9370, 5.9310, and get here x dash. Simplification as 2.4469 plus 8 0, 5.93. So this dryness fraction is. Now we know dryness fraction at 0.1, sorry, at 0.2 as well as 2 dash. So we can find out enthalpy at 0.2. So H2, enthalpy at 0.2 is given as HF2 plus 2 F, enthalpy of wet steam, that pressure of P2 which is equal to 3 bar. So these values we have to take from steam table at 3 bar. So coming back to the steam table at 3 bar, enthalpy of liquid at 3 bar is 561, so that we can see in this table bar 561.45 HF1, and this is sorry HF2, and this is HFG2. So taking these values, so HF2 is equal to 561.45 plus H2 value is we have obtained as 0.876 point into HF2 value is 2163.85 at pressure of 3 bar. So on simplification we get this as 561.45 plus of 0.876 into 2163.85. So this will be 456.98 kilojoule per kg. So by graphical method we can obtain this as by using Molier chart, so that we have obtained is 2460 plus 20. We obtained it as 0. Directly we obtained this value here. We obtained it by using, so again H2 dash equal to F2 dash plus 2 dash into F dash F2 dash at pressure. This is at pressure of at pressure 1.2 bar. 1.2 bar. We can take the values. You can see back pressure PV is equal to 1.2 bar. So enthalpy is 439. Enthalpy is 439.40. And heat of vaporization 44. We can substitute it equation and can find out enthalpy at point 2 dash, pressure of 1.2 bar, 439.4 plus of H2 dash 0.83. Reynolds fraction is 0.83 at point 2 dash. 83 into 2244.10. On calculation, get this value as 439.4 plus of 44.02 point 00 per kg. So now this value we obtained by using their chart also. Their chart we obtained value of H2 dash is plus 20 here. So the chart 20 plus D. So in this way you can find out these values of enthalpy 0.1, enthalpy at 0.2, point dash Euler chart, or using analytical method by using a steam table. So one and the same. Only thing is the answers will differ in the accuracy. So now again we will find out work done here. Work done 1 equal to h1 minus dash. H1 value we obtained here is by graphical method 2797.37 797 797 minus of H2 dash enthalpy at point 2 dash 2302 02.3. So this value dash 02.3 02003. Work done 1 week and like this 797.02.003. Work done here in this critical 495 kilojoules per kg. So in graphical method we had obtained it as 480 kilojoules per kg. Now work done 2 obtained like this 1 minus H2. Work done from H1 to H2, then PdV work plus of specific volume at 2 into P2 minus PB to 100. One value we know 797.7 minus of H2 value we obtained here. Analytical method is 2456 456.98 456.98 plus of specific volume 2 pressure 3 bar 0.6 that we have already taken it from steam table 0.605 into pressure 3 minus of 1.2 100 on simplification get this as 2 minus plus of 449 4 kilojoules per kg, but by graphical method we obtained this work done to 448. Now we know work done 1, work done 2. Rankine efficiency has to be obtained. So obtained Rankine efficiency, heat supplied has to be calculated. Supplied again here H1 minus HF4 1. Already we know that 797.7 minus HF4, same value that we have from steam table 448.9. Sorry, HF4 as 439. This was taken from steam table. steam table at pressure of 1.2 was taken table at 439.4. Same value we will take here 430.4. Supplied will be 7 and 7 7 minus 39.4 will be 3 7.97 kilojoules per kg. So this was obtained by graphical method. Heat supplied obtained by graphical method was 0.6 comparison. Now percentage loss, or before that we wrote Rankine efficiency 1 and Rankine efficiency 2. Rankine efficiency 1 equal to work done 1 divided by heat supplied into 100. Work done 1 is 495.86 obtained here, divided by heat supplied is 57.97 to 100. Rankine efficiency 1 can be obtained as 495.86 divided by 2, 57.97. Rankine efficiency obtained analytically 21.02 first Rankine efficiency. Then second Rankine efficiency can obtain Rankine efficiency 2. Work done 2 divided by heat supplied to 100. Work done 2 is 449. 449.24 whole divided by heat supplied is 257.97 into 100. This gives us Rankine efficiency 2 as 449.24 divided by 257.997 with 19.05%. So this efficiency, Rankine efficiency 1 by graphical method was 20%, was 20.33%, and 2 was 19.1, 0.33 and 19.01. 20% it was by graphical and 0.01 and by graphical method. So these values in bracket are representing results by graphical method. You can see the error. Now we'll find out percentage loss in work. First of all, we will carry forward the work and Rankine efficiency on next slide. Work done 1 equal to 495.86 kilojoules per kg by analytical method. Then work done 2 analytical method was 449.24 kilojoules per kg. Then Rankine efficiency 1 is 21.02 percent, and Rankine efficiency is 19.05, and percentage loss of work. Find out loss of work W1 divided by W1. Percentage loss of work is WD1 is 495.86, 449.4 divided by 25.495. Four four nine point two four divided by 459.4%. 4%, which was in the first case in graphical method, the work loss percentage work loss was calculated as 6.47, 787. Then percentage loss of Rankine efficiency. Rankine efficiency 1 minus Rankine efficiency whole divided by Rankine 1 Rankine efficiency 1% minus 5 Rankine efficiency obtained by analytical method whole divided by 21.02 into 100 as 2 minus 5 whole divided by 9.37. But by graphical method this was approximately 49.49. There is error here. There is error. You can find by graphical method 0.47, analytical method loss is 4. So which one is accurate? So accuracy which we have obtained by analytical method is more accurate than graphical method. Graphical method does not yield more accurate answer as compared with the analytical. Here we have compared both graphical method and analytical method. Now we can summarize this data table. Here we will prepare a table. First one, graphical method, and analytical. First we obtained h1 value. What was h1 value? Both the cases. 2800 796. 2800 197 kilojoules per kg. Kilojoules per kg. Then we obtained h2 value. Value in first case h2 value is 2460 2456 46 per kg 56.98 per kg. Then we obtained h2 dash. By graphical method we obtained h2 dash as 2320 joules per plus 302.001 joules per kg. So 2.003, it is 0.0. We obtained work done 1 was 480. Second we obtained 490. 480, 490. 5.86 joules per kg. Then work done 2. We obtained graphically was 448.9 joules per kg. 4.24 per kg. Then work done, heat supplied in both cases. First case it was 2360.6, 0.6 graphical. Analytically we obtained heat supplied as 57.97, 57 per kg. Then we obtained Rankine efficiency. First case was Rankine efficiency 20.33, 21.02, 20.02. Then Rankine efficiency we obtained. Rankine efficiency was 19.01, 19.05, 0.01, 19.0. So this is comparison. Then loss of work, percent loss of work. First case it was 0.47, 9.4, 9.4. Is loss of was 6.49 by graphical method. Analytical method was 7%. Table indicates differences comparison of method with analytical method. Same problem we have simplified methods. One by graphical method and second by analytical. So compare these results. Graphical method is 2800, here 2797, approximately close. But the results which are obtained by analytical method are more accurate compared to graphical method. But the graphical method is more quick. So I hope you understood the method of using steam table chart to simplify the problems on vapor power cycle. And here this work is lost due to incomplete expansion of steam. So how much percent of work is lost due to incomplete expansion? Analytically 9%, 0.4% work or efficiency is lost by 9.37%.